All right, we are back for part 2 of this scintillating, mesmerizing presentation of the Work Energy Theorem. You might even say it's riveting. Of course, I'm sure that if you were a welder working on a skyscraper, you would find that work very riveting. Teacher joke. All right, let's look at example 5.10. Here we have a circus acrobat dropping from a height of 2 meters onto a springboard. And it's going to compress a spring underneath the springboard. We can say that she begins with a certain amount of potential energy, but that potential energy is going to be the sum of the height above the board plus the distance that the board is going to be compressed. So let's just modify the potential energy formula a little bit here. So her total height is an h plus d. Now, where's all that energy going to go, assuming no loss of energy to air friction and no loss of energy due to heat when the spring gets compressed? And so her potential energy is going to do work on the spring, and that work is 1/2 k x squared. But in this case, x is just d. So I'll get rid of the x, and it's just d, because that's when the spring begins to become compressed. And now we are going to solve this problem for d, and as you might anticipate, with a first power here, second power there, you're going to expect a quadratic equation, but you guys can handle that. And so that wasn't as hard as it looked. When you use the work energy theorem, and the approach again that I like to take is I like to start off with all the energy in the system and then see where it goes along the way. You may not think this way. You might want to think more in terms of the way the book does, but this is the way that I like to break the problem down. It's up to you. So let's clear this off. And now let's look at example 5.11. In the text, 5.11, here we have another conservation problem, and we have a block that has been pushed up against a spring. So you have stored energy in the spring, potential energy stored in the spring. And where is that energy going to go? Well, it's going to move the block across the horizontal surface. Then it's going to move the block up the inclined plane. And so the parts of the problem are A, find the maximum distance that the block travels up the frictionless incline. And then how fast is the block going at half its maximum height? So we take our total energy to start with. The total potential energy stored in the spring is 1/2 k x squared. And all that energy stored in the spring, remember, we don't need the negative sign in here because we're not talking about direction, just the total energy. And all that energy is going to be converted into potential energy, moving the block up the plane. And in this case, we're going to be solving for h to find the height up the plane. And then once we know h, and since we know theta, we can find the distance along the inclined plane. We're trying to do this distance here, but you know h and you know theta. So a little bit of sine theta, you can solve this for d. And just as a reminder, read the problem carefully to discern whether you're looking for this or this. Now let's make this problem more interesting. What if we're only going halfway up the plane and we want to know how fast the block is going halfway up the plane? Well, then that means that, what's going on there? There we go. That means we're going h over d, 2, excuse me, is the distance up the plane. And all the rest is its kinetic energy. So that problem is not nearly as hard as it might look. We could also then say, what if there was friction along the horizontal surface? Well, if there was friction along the horizontal surface, we would say that some of my original energy has to overcome that friction, which would be the force of friction along the horizontal surface times the horizontal distance, which I'll call x. So this is horizontally. And then we could say, what if there's friction on the inclined plane? In which case, we can also add then a component for the force of friction on the inclined plane acting along the distance that it moves up the plane. And as long as you're keeping x and d and h straight, the problem is not nearly as hard as you might think. All right, let's move on to another problem. And this time, let's and I'm moving through the pages in my book. And actually what we're going to do now is cover the last idea in the chapter. And that idea is the concept of power. So I am going to empower you at this time to dig into this concept and master it. You should know that power is the rate of doing work. The rate of doing work. If I multiply, if I remember that work equals force times distance, now I have power equals force times distance over time. And if you know that distance over time is velocity, you get equation 5.25, the instantaneous power, based upon force and the velocity. What are the units of power? Well, you have the joule per second, and we call the joule per second a watt. And the watt is named after James Watt, one of the guys who helped us to understand that power and work were different. So if you didn't hear me, what? It's just the unit of work divided by time. You might also recognize that when we get to electricity, next April 12th, we're going to talk about the kilowatt, and then we're going to talk about the kilowatt hour, because the kilowatt hour is how you're charged in your electric bill. Obviously, a kilowatt hour, if kilowatts are joules per second and hours can be in terms of seconds or time, the units of time cancel out. And so when the electric company charges you so much money for every kilowatt hour of electricity you use, they are actually charging you for your energy. They're charging you for the joule. And typically, it costs anywhere from maybe 7 to 12 cents per kilowatt hour of electricity that you use. So I'm going to erase this. And I don't like all these spurious marks. There we go. And now I'm up to page 146. Actually, I'm going to go back to 145 so I can read the problem. And here we have the good old elevator again. A couple of people on the elevator. And we have a constant frictional force. That's going to use up some of that energy. What minimum power in kilowatts and in horsepower must the motor deliver to lift the fully loaded elevator car at a constant speed of 3 meters per second? You'll see the free body diagram. You'll notice that we've got the force of tension acting up. Here's the elevator with the people in it. You have the force of weight, which we'll say is the weight of the individuals and the elevator itself. And you also have the force of friction acting down, because in this case we are trying to go up. And you'll notice that we're accelerating upward at 3 meters per second squared. That means my upward force of tension, minus my downward forces, the force of weight plus the force of friction. Those are the downward forces. There's my up force minus the down force, must equal not 0, but ma, because we're accelerating upward. And conveniently, they give us the acceleration. And that's how you would set up this problem. When you're trying to find the work that is being done, you recall the earlier equation, and now I'm moving ahead in the page to page 146. And you'll notice towards the end, they remind you that power equals force times velocity. I'll change this so it looks just like the book. And so you have the net force and you have the velocity after 1 second, so you can find your kilowatts. Now, by the way, the old-fashioned unit was called the horsepower, or really lowercase. And this was actually a standardized unit, not too many sig digs, obviously. If you had your so-called average horse, how much work could it do per period of time? And that was defined as 1 horsepower. And on a previous page, back to 145, that horsepower is 746 watts, which, in other words, is approximately 3/4 of a kilowatt. So there's a rough conversion factor if you're going to convert it into horsepower. Now, in the United States, we still have lots of cars where we talk about the horsepower of the engine. Now, my car probably has a horsepower, maybe 50 or 75 horsepower. But if you get a souped-up muscle car, you could be 100, 200 horsepower easy. You'll also notice that if you wanted to convert kilowatts into joules, a kilowatt hour into joules, kilo is 10 to the third, and you also have 3,600 seconds in an hour, 60 times 60. And so you get 3.6 times 10 to the 6th joules, or 3.6 million joules in a kilowatt hour. Now, a joule of energy would be kind of like if a bug buzzing around were to not adjust its speed well and crash into your cheek. That would be about a joule of energy, pretty small number. And of course, if that bug was a mosquito, well, you hate it when that happens. Now, I'm going to skip this last problem with killer whales. Pretty straightforward again. You've got a change in kinetic energy. Once you find your kinetic energy, you divide by the 6 seconds over which the change took place to find your watts. Here's a speedboat power problem. Again, these are not terribly difficult. You'll notice in this problem, we're at 5.14 on page 147. In this problem, you have your change in kinetic energy. And notice that we transition, once we find our velocity, into using our old kinematic equations from chapter 2. All right, I want to finish the chapter here quickly. I'd love to be able to do some center of mass problems. Let me erase my screen here. Again, all these spurious marks have to go. One of your vocabulary words, right? Spurious, maybe? Indubitably. So, center of mass, I have a bunch of demos that I'd like to do to talk about the center of mass. You could maybe look at some of the demos for the center of mass on YouTube. I'm just not there to do them for you. But the center of mass would be, which we've been using all along when we do our diagrams. For example, if I had a block on an inclined plane, we drew all of our vectors from the imaginary center of mass of that block, rather than talk about the fact that the weight is distributed over the entire surface. We just drew one vector, and technically that vector would be operating from the center of mass. Now, if an object has uniform density, the center of mass would probably be at the very geometric center of that object, assuming that the object is a geometric solid. In your body, if we were to assume a relatively constant density of the human body from head to toe, your center of mass would be a little bit different. Male's center of mass has a tendency to be a little bit higher because of broader shoulders. And for ladies, the center of mass has a tendency to be a little bit lower because of wider hips. Now, the work done by a varying force. And now I'm on page 149 trying to finish up so I can get this posted. If you're looking at the graph, it looks sort of like this. It's hard to draw straight lines with an Apple pen. It's not too bad. And we have this curve. You should recognize that this is the force, and this is the distance that the force is being exerted. You might recognize that the slope is F over X. So if this were the force being exerted on a spring, this would be your spring constant in newtons per meter. But you should also notice that the area under the curve is going to equal some value, let's call it K, times force times X. And therefore, that is going to equal the work done. So as you exert a force, and that force changes, it's bigger, it's smaller, it lessens, it increases, you continually stretch the spring towards the right, the area under the curve is the entire work done in stretching the spring over that exercise. And now the goal is find the area under the curve. Now, obviously, you could use calculus and take the integral. But, we could do something like this and say, let's imagine I drew one box, right? And I can find the area of a rectangle pretty easily. And you'll notice that in this box, I missed some of the work right there in the upper right. And down here, I included stuff that wasn't actually part of the work. And I'm hoping that these two values sort of cancel each other out. Now, I can improve the situation if instead I make two boxes. Maybe I make a box right here, and maybe I make another box right there. And now I have a little bit that I have missed and a little bit extra. And maybe this is a more reasonable amount. Well, I can also then, let's say, have more boxes. Maybe I can have this box here and this box there and this box here and so forth. The point we're making is that as your change in x for your width of your box approaches 0 or gets smaller and smaller and smaller, you're going to have a more and more precise measurement of the area under the curve. That's basic calculus. Now, obviously, if you're doing a constant amount of work, and remember, the word for today is spurious. These are all spurious marks I have to get rid of. If your curve looks like this, you're certainly not going to need calculus. All you're going to do is say, oh, I'm just finding the area of a triangle. So it's going to be 1/2 f times x. And that's going to be equal to the work. And I'm going to conclude there. That concludes our chapter. Hopefully you'll read through it a little more carefully. I tried to hit the highlights.